Hello and welcome to LogicBot. This is going to be the first lesson in the first course on understanding the basics of machine learning. In this course, we're going to dispel a lot of myths and rumors about machine learning. And in this video, you're going to learn about real-world machine learning. This entire course are going to be must-know machine learning concepts. And I guess I should put down here for the real world. All right. Don't care what happens in academia. That's not the real world. Don't care what they say on boards like Quora or Reddit. They have no idea what they're talking about. All right. So this is must know machine learning concepts. Moving on. So in this section, all right, not the course, this is just this first section, we're going to talk about the AI hierarchy. Artificial intelligence is hierarchical, and you must know what that is. We're going to define AI, because if you can't define AI, how are you going to work in it? Well, you're not. How about we're going to define machine learning? Machine learning lives under the AI hierarchy. Where does it fit in the AI hierarchy? Yes, you're going to have to know that. What is a good definition for machine learning? Yes, you're going to have to know that. All right. So what's an algorithm? All machine learning models are algorithms, right? Oh, didn't mean to cross that out. Meant to underline it. All right. So they're algorithms. What's an algorithm? What are the core branches of machine learning? All right. What are the use cases for machine learning, right? The different types of models. We have deep learning models on one side, and then we have traditional trad models on the other side. When do we use deep learning models versus when do we use traditional models? All right, classification. It's the top model used in the real world. All right, what is it? And what model do we use? Now, we know what model to use for classification and regression problems. We know the top model. What is it? All right, let's move on. Artificial intelligence is hierarchical, right? There is a top, and then we move down, and then we move down. All right, it's hierarchical in nature. Here is our hierarchy. Kind of looks like an alien, huh? All right, so up here we have AI, right? He is the top of the artificial intelligence hierarchy. Now, don't worry, we're going to define these in a second. Right now, I want you to understand and memorize the hierarchy, because if you don't understand the hierarchy, then the definitions are useless. Under that, we have machine learning, right? Machine learning lives under AI, right? AI is top, machine learning is second. Over here, we have trad models, trads, and then we have deep learning models. All right, so traditional models are machine learning models. Deep learning are machine learning models, and there is a difference. Most of the real world is about traditional models. It's not about deep learning models. If that's the case, then why does deep learning get all the credit? Because all the cool stuff is happening with deep learning models. These traditional models are what's called a solved problem. All right. All right, so we've got our hierarchy. So AI, ML, traditional models, deep learning models. And we go deeper here if we wanted to. We could put little zeros here. And what are traditional models? We're going to talk about XGBoost. What are deep learning models? We're going to talk about CNNs and NLPs. All right? All right, so we've got this hierarchy, and you must know it. All right, so now that you have this hierarchy in mind, let's move forward. So now we're going to define AI. So a computer system is capable of performing complex tasks that historically only humans could do, such as reasoning and making decisions or problem solving. Yes, that's great. And this is a Google definition. This isn't something I made up. So why should we use Google for our definitions? Because that's a crown, if you didn't know. They are the king in the machine learning space. Right? That's why we use Google definitions. So we need an agreed upon set of definitions. You just can't make your own up. If I were interviewing you and I said, hey, can you define AI? And you make something up, then the interview's over and you can go home. All right. So now this is a little verbose. This is a little long, isn't it? So let's cut this down. Computer systems. Well, we know they're computer systems. Computer systems capable of performing complex tasks. Okay, that's true. How about computers? How about computers? Now, we're watering this down so we can remember it. We're putting this in our own words, or for this example, in my words, so I can remember this. You're going to have a lot to remember. Technical interviews are very stressful, and you're going to have to know all this stuff. So computers capable of performing complex tasks. That sounds pretty good. That historically only humans could do. Yeah, well, we know that. That historically only humans could do. That's verbose. We don't need it. Computer systems capable of performing tasks such as reasoning. Yep. Making decisions or solving problems. All right, that sounds pretty good. I like that. And again, this is my own words. Well, these aren't my words. It's Google's definition. But what I'm doing is watering it down so I can remember it for an interview. Let's see. AI is defined as computers capable of performing complex tasks such as reasoning, making decisions, or solving problems. All right, that's something I can remember for an interview. That is what AI is. Moving on. Machine learning. All right, what is machine learning? We need a definition for it. Can't make it up in the interview. That won't go well for you if you do that. Machine learning is a subset of artificial intelligence, and we saw that when we looked at the AI hierarchy, didn't we? That focuses on building systems that learn or improve performance based on the data they consume. Again, this is a Google definition, and I don't really like it, but we're going to use it. So, machine learning is a subset of artificial intelligence. Well, we don't need to tell anyone that. That focuses on building systems that learn. Machine learning focuses on building systems that can learn. All right, yeah, let's do that. Let's keep focuses. So let's keep focuses. We're going to keep you focuses on building systems that learn. All right, I like that. How about or improve performance? Well, of course, we're going to need to improve performance. That's ridiculous. All right, machine learning. Machine learning is building systems that learn. All right, we need this is back too, don't we? Is. We'll bring you back is. And improved performance is gone. Sorry, don't need you. Verbose. Based on the data they consume. All right, this is really important. You see that? Data. All machine learning models. Are you ready? Hear what I just said. All. I didn't say some or one or two or 90%. I said all. Every machine learning model was past data. Every single one. There is no machine learning model, right? None exists that aren't past data before they make a prediction. All right. All machine learning models are past data, this guy, that make predictions. All right. That's what machine learning models do. All right. So we have our watered down definition, and I kind of like it. Again, you're going to have to water it down in your own words, and you're going to have to take notes, right? What is AI? And then what is ML, right? And then take some more notes. And you're going to have sentences and paragraphs that make sense to you that you can memorize for tech interviews. Tech ins. Because they are stressful as hell. All right? Machine learning are algorithms that look for patterns in data. Yes, they are. All right. What do we call these algorithms? We call these algorithms models. We don't call them algorithms. We call them machine learning models. And what do? They look for patterns in data, and that's all they do, right? That is every machine learning model in existence. So please don't ask me about machine learning models that do X, Y, and Z. This is what they do. Every single machine learning model in existence, whether it's ChatGPT or full self-driving or anything you can think of, if it's a machine learning model, it does this. And that's the key. All right. So machine learning models are algorithms. All right. So we call them models. Great. Moving on. We've got that. That was pretty straightforward. All right. We refer to these as models. Yes, we do. I just said that in the last slide. So we can probably move forward from this slide. So what is an algorithm? A set of rules, all right, to be followed in computations or other problem-solving procedures. So think of an algorithm like a recipe. It's a series of steps used to solve a particular problem. All right. Again, if you don't like this definition, go find one. Go use Google. Go to your favorite Google and then look up, right? Google, what is an algorithm? I'm not spelling that out. What is an algorithm, right? And then find one you like and use your own definition. But it's going to have to be a definition that's widely accepted or known. It can't be something you fabricate. All right? So we have two core branches of machine learning. We'll call these machine learning branches. We have traditional models and we have deep learning models. Now, under here are ANNs, or artificial neural networks. Now, these are different than deep learning models. What's the difference? Well, it's a little deep for this lesson, but the difference is in the number of hidden layers. And these hidden layers, we've got the input layer and we've got these computational layers. These are called hidden layers in our neural network, right? So we have an input layer, that's the I for the input, and we have an output, right? O for output. And in the middle of our deep learning model, we have these things called hidden layers. All right, we'll talk more about that, but I wanted to tell you the difference is the number of hidden layers. So if someone says, well, what's the difference between deep learning models and an artificial neural network? The answer is the number of hidden is the key, layers, because these input layer and the output layer are also layers, but they're not computational layers, right? 80% of machine learning is not deep learning. 80% of machine learning in the real world are traditional models. All right, that's hard for a lot that are new to the space to absorb, but it is. That is the facts. So what are some use cases? When will we use traditional models versus deep learning models? Well, at a high level, there's an easy way to understand this. For traditional models, we're going to use structured data. What's structured data? It is data that looks like an Excel spreadsheet. It's in the forms of columns, right? Up here, we've got columns and we've got rows, right? That is structured data. That's what that is. Over here, we have deep learning models and we have unstructured data. Well, what's unstructured data? Well, it's data that doesn't easily fit into this matrix or this array or this table-like structure. Well, what's an example? How about an image? An image does have structure, but it doesn't easily fit into an array. Well, how about an audio file? Same thing, right? Has structure, doesn't fit into an array easily. How about text? Yep, text is another example of unstructured data that does not fit well into tables. So your question may be why? Why is so much machine learning structured data? And that's because of this thing called a database, right? He is a DB. And this is where most companies store their data. And that's why they have tons of this stuff laying around that's not been touched, right? They don't have tons of this stuff laying around yet, all right? That's why. All right, so for our entry-level conversation, just remember that we've got this hierarchy, right? We've got AI out here, right? If we draw a big circle around here, we'd have AI, then we have machine learning models, and then we have traditional models, right? And then we have deep learning models, and they have their own use cases. So structured data, right? Unstructured data, and then be able to give a few examples of what they are. So structured data is a table in an Excel spreadsheet. Structured data is a table in a database. And then we've got different databases, right? We've got OLTP, and then we've got data warehouses, right? And this is why this is now one of the top requirements for machine learning engineers, right? This is actually hard. This is what you're going to spend most of your time working with. Pulling the data out of these databases and making it modelable. It is a pain in the ass. Moving on. Structured data is data that's in the form of an array or a matrix. All right, we just touched on that in the last lesson. All right, so structured data is in an array or a matrix. Why? Because we give it structure. All right, here's our table in a database. We say in this column, we're going to hold numbers 1, 2, 3. These are integers. So we tell it when we define this table, we say in the first column, the only thing we're going to allow are integers. Next, maybe dates. So the only thing we allow here are dates, right? 11, 24, whatever. That's a date column. And this may be varchar or characters. Maybe we're going to allow characters in this column, right? We define each of these columns. That's why it's called structure. It's easy to work with. This is like a table in a relational database. And what makes this easy for machine learning models is that it's in the form of a what? An array. And an array is the object that almost all machine learning models use. Your data must fit into an array if you want to use it in a model, a machine learning model. Now you may be thinking, well, what about images? Yep, broken down into arrays. Yes. What about text? Yep, it's all broken down into arrays. All right, moving on. Most applied machine learning is on structured data. Again, to the tune of around 80%. That's what Google says. I think it's more than that. Structured data is data in those databases, right? We've got tons and tons of these databases, these DBs laying around everywhere. And there's data in here, and most companies don't even know what they have, right? So once the problem has been defined, it's going to be up to you, the machine learning engineer, to go in here and make sense of that. And you will find that it's quite a challenging task. Most applied machine learning is classification and regression. These are the type of problems you're going to see, right? Classification and regression problems. And most really is classification, right? And this is on structured data, on struct. All right? Classification, models, classification, is grouping objects into two disparate categories. All right, so we've got a machine learning model, and we've got dogs, and we've got cats. And we want our machine learning model to look at these columns of data about our dogs or cats and be able to tell us, is, after they look for patterns in this data set, is it a dog or is it a cat? Now, this makes this a binary classification problem, right? Because the answer is a 1 or it's a 0. It's a dog or a cat. That's it. That's all it can be. So what might we have in these columns? I don't know. Maybe the size, right? The size, maybe the first one, like how big. And I think as a general rule, we're going to go with house cats here, so dogs are bigger. All right. So what else might we have? Tail. Well, they all have tails, so I doubt that's going to help us, right? But maybe we have that information anyhow, right? Maybe their foods. What do they like to eat? Again, and this can go on forever, right? We can have all this information we want, and we want the model to be able to go here, look at these patterns, right? Look at each one of these patterns and say, yes, it's a dog or it's a cat, right? And we wanted to tell us dog 1 and cat 0. And that's what we want our machine learning model to do. All right, so classification is grouping objects into disparate or separate categories, right? Here we're only going 2 categories, 1 category, 2 categories, all right? That's called a binary, I think we'll see that in a minute, binary classification problem. There are 2 types of classification problems. There are binary, multi-class. What's a multi-class then? If binary is a 1 or a 0, if it's a cat or a dog, then what's multi-class? Well, cat or, oh, I cannot write, can I? Or, that's an R. Dog, or how about a bird? All right, now we don't have 2 classes, now we have 3 classes. That makes that a multi-classification problem. All right, multi-classes, right? Not 2, all right? More than 2, all right? Linear regression is predicting points on a line. We've got a graph. We've got our X and Y axes. We're here, and we want to know what that is right there, right? We want to know that point. So that's linear regression, all right? Linear regression is predicting points on a line. All right. For our conversations, we're making it as simple as possible, right? We want you to understand it and be able to regurgitate it to someone in an interview. All right. Most of the time, they're not going to ask you for the formula of a linear regression model. They're going to want you to know, well, what is linear regression compared to classification? Tell me the difference. Which one's used the most? What model would you recommend for these? All right. The top model for these problems are traditional models for classification, right? For classification and for regression problems, all right? Traditional models, not deep learning models. You can use deep learning models, but they're not the best model. The top model class for these are called gradient boosters, right? So the top model class for regression and classification problems is gradient boosters. Well, how do we know that? Well, we have competitions, and they've been around for a long time. One's called Kaggle, right? And Gradient Booster is actually one called XGBoost, has won almost every single structured data problem. Every one. All right. So that's how we know that if we're using classification and regression, we know XGBoost is going to do well. It's going to beat deep learning models. It's going to beat SVCs. It's going to beat everything else, right? Not only that, we have these companies, we call the top three. We have Google, we have MSFT or Microsoft, and then we have AWS, right? Amazon. And these are our top cloud providers. And these are companies who are very vested in machine learning. Well, what do we know about these companies? If we did a little research, we would know that on all these problems, we would know that on regression and classification problems, sorry, my handwriting's atrocious. Regression, that's regression classification. We know that guess what they're using? Yes, all three are using Gradient Boosters. And the top one is actually Google. They use a service called AutoML, and they use Gradient Boosters to find the model answer, so to speak, or to find the prediction for the model. And then in order to find the hyperparameters or parameters that you pass into these models, they use deep learning models to find the best. And it was back tested on all the Kaggle competitions, and I think it came in first or second. All right, so that's another reason or another way we know, right, through testing and through the services these companies use for their clients, we know that Gradient Boosters are the top choice for classification regression models. All right, so how do we know the top model? So we just give that. I kind of jumped ahead to the slide, didn't I? Here I just said, well, we know it because of Kaggle, and I just gave you an overview of why we know it. Yes, Kaggle has given us the answer. All right, so what do we learn in this very first lesson on applied machine learning or real-world machine learning? We learned the AI hierarchy. Yes, you're going to have to know it. Yes, you're going to have to go AI. Yes, you're going to have to understand machine learning. Yes, you're going to have to be able to regurgitate this. Yes, you're going to have to know that there are deep learning and traditional models. Yes, you're going to have to know what the use cases are. Right? We talked about AI and gave a definition for it. We even watered that definition down. Yes, you're going to have to give a real-world definition if someone asks you in an interview what AI is. If you make it up, you're going home. You're going to need to give a real-world definition for machine learning. It's one of the first questions we ask in our machine learning interviews. Algorithms. You're going to have to know what an algorithm is, right? What is an algorithm? You're going to have to give an example. Again, the recipe is a very common one. Right? So you're going to have to know what an algorithm is. You're going to have to know that we don't call them algorithms. Right? That's not machine learning vernacular. We call them models, and you're going to have to use that term. We talked about the core branches, right? We talked about deep learning and traditional models. We talked about machine learning. We talked about some of the use cases for deep learning. We've got over here traditional, we've got the structured data, and then over here we've got unstructured data for deep learning models. We talked about use cases. We said that most machine learning is on structured data, and most machine learning is, or is most machine learning are? No, it's most machine learning or is. No, it's most machine learning is, I think, because machine learning is singular. Most machine learning is, you can correct me if I'm wrong. Most machine learning is 80% of it, so to speak, is done with trad models, traditional models, and we know it's XGBoost. Again, maybe not XGBoost, but a type of gradient boosters, and the most widely known is XGBoost. I use it all the time. It's one of the few models I use all the time. We know that the use case for XGBoost, right? We know that we've got classification regression, and we know that classification is probably number one. This was some guy at Google who said this based on looking at the people that are using their cloud services for machine learning. He said classification was a large part. He didn't give a percentage, but I remember him saying it was a large part of their models. All right, so we know classification is used a lot. All right, so now you have some basics, you have some conversation pieces, and you have some things that are going to be necessary for you to know and be able to regurgitate in a technical interview. It's going to be a lot thrown at you, and you're going to have to remember it. So take notes, write it down in your own words, right? And understand all of this.